You have started and allow the audience to come in.
Good morning. This is Bob St. Clair representing our group here at Stanford University. This is Stanford EMX seminar, the second one of the year 2021. And once again, we have two superb plenary speakers today who are going to tell us different aspects about TEM and indeed STEM. So in the interest of time, I think we should get going right away, and I'll pass the baton to Hua Chu, who will introduce Bob Glaeser, and then halfway through we'll pass on to Yi Che, who will then introduce Dave Smith. So Hua, over to you, please.
While you are on mute.
Okay.
Is Hua there?
Yes, I'm here.
Okay.
Hello, this is Hua Chu. It is my great pleasure to introduce our EMX Symposium series speaker today, Professor Bob Glaeser from Berkeley National Laboratory at UC Berkeley. Bob is truly the initiator of the field cryo-electron microscopy. He has often been called as the grandfather of the field. Bob conceived the idea of keeping a biological specimen at liquid helium temperature in a transmission electron microscope. He thought that would be the solution to overcome the barrier of keeping the biological specimen intact by keeping it frozen hydrated, and at the same time will reduce the radiation damage effect at low temperature. His conception going to low temperature in TEM has created the field of cryo-EM. His innovation has earned many honors and recognition, including the election to the US National Academy of Sciences. I personally appreciate Bob as a mentor because he does his research not because it's easy, as many of us tend to do, but because it's scientifically worthy. His research is always based on science physics principles. Today, he's telling us another innovative approach he has been undertaken, how to improve the image contrast by using a phase plate in the electron microscope. Let's welcome Bob.
Thanks very much, Hua. Thanks very much to you and Bob for organizing this. It's a very exciting series of talks. I'm honored to be part of it. The title is for today's Development of Faceplates for Transmission EM from 1947 to present. I'm not going to say much about 1947, but that's just a kind of a placeholder. When the first paper was published relating to in-focus phase contrast with a faceplate in the transmission EM. Using a faceplate can provide the most information about biological samples of all of the information that's present in the exit wave. Nearly all of it can be recovered if you have a faceplate. Now, as background, to make sure that we're all on the same page, and I've got a little bar. I'm going to try to. No, I don't want to leave the meeting. All right. I've got a bar on the bottom of my screen that's annoying me and interfering with my being able to see what I want to talk about. A perfect Zernica faceplate would recover nearly all of the modulated signal, as I just said. And as background, the image of a slab with waves coming into it, at every point in the specimen, the wave has the same amplitude and the same phase if we illuminate with a plane wave. On the red line, the exit wave For biological objects, the intensity hasn't changed in passing through the specimen, so the amplitude of those peaks is the same, but you notice that where the wave peaks and goes through zero has shifted depending on where the electron beam has gone through the object. And those modulations in the phase of the transmitted wave carry nearly all of the information. Now, the Zernike phase plate is a device that the optical diagram on the right shows a lens. The beam that goes straight parallel to the optical axis is focused at center and passes through a hole. The beams that are scattered pass through the plate, and the two should be shifted by 90 degrees in order to convert the phase modulations into intensity variations in the object. That's the principle of the Zernike faceplate. And Birch in 1947 proposed 3 different ways to make that happen in the electron microscope. The first 2 are ones that have been tried. The third one has never been tried. I'm not even sure how it works, but that's all part of history. Now, in 2013, I published a review article on many different ways in which weak phase objects can be imaged in the electron microscope. And at that time, I came up with 18 different ways. I'm not going to talk about all of those. I'm just going to pass through the history a little bit. Defocusing the bright field image, which is the first example on the right-hand panel, defocusing the bright field image is a very good way to image a weak phase object. It's what light microscopists used to do before phase contrast came around, and it's what cryo-EM people still do today, and they're not even sure that a phase plate is needed. So defocusing is a very good way, but I will address the question that it can be improved upon by a great deal. Other ways of imaging wake phase objects include dark field imaging. STEM is the best way to do that. Tychography, biprism holography. Then highlighted in blue again is faceplate devices. What I'm really going to be talking about. Included in faceplate devices is the middle panel on the right figure. Looks just exactly like the Zernike faceplate I talked about. Also using some kind of microfabricated electrodes to localize the electrostatic potential, or inserting a knife edge that's called Foucault or Schlieren optics. All of the things that are grayed out are very inferior to just defocusing the bright field image. And faceplates, for the most part, have not worked well. But there is one faceplate called the VOLTA. It uses what is called the VOLTA potential, or it's called the VOLTA faceplate on the upper right-hand corner. That has also been called a hole-free carbon film. You just put a carbon film in the back focal plane in the diffraction pattern, and I'll say a little bit more about that. Then finally, concluding this summary slide is what is called the ponderomotive faceplate. It uses a laser beam to apply a phase shift to the unscattered beam in the electron microscope, and that will be the main thing that I talk about. Just some more background before I actually get into talking about the laser faceplate. I want to emphasize a little bit more about defocus-based phase contrast. It provides only a poor realization of what might actually be possible. And the lower right-hand panel shows what a simulation is of what the image would look like without defocusing or without a faceplate. In the middle, if you defocus the image, and on the right is if you have something like a Zernike faceplate to image the object. The problem with defocusing the image is wonderful, but, and in fact, the wave aberration that corresponds to spherical aberration and being defocused, that wave aberration is a faceplate. The only problem with it is that the amount of phase shift varies a lot over the spectrum of scattered beams, and the amount of phase shift varies depending upon what the defocus is. And as a result, there is a phase contrast transfer function, which has a nice flat region over much of the frequency spectrum in so-called Scherzer defocus. But at very low spatial frequencies where you really can see the object, there is very little contrast. If you defocus more, you can get more contrast at low spatial frequencies at the expense of introducing oscillations. These things are all well known to all of us, but I wanted to enumerate them before launching into the real thing that I want to talk about. Now, the VOLTA faceplate I mentioned before is the best realization of a faceplate to date. And the way that a phase, a Zernike type phase difference is produced is when the electron diffraction pattern in the back focal plane is put onto a thin carbon film. The strong unscattered beam causes some kind of a charging effect. We don't really know what that is. It's not contamination. It's not the usual charging artifact. And Danev referred to it properly as a VOLTA potential. It's a surface potential. It's probably some kind of a dipole sheet produced in the area of the illuminated beam. And this surface potential builds up with time the longer that spot on the carbon film is irradiated. As a result, the phase shift, the desired Zernike type phase shift in the upper panel increases with time as exposures go on or as you record more and more images. The amount of phase shift gradually ramps up. So at first it's quite a small amount. It eventually reaches 90 degrees phase shift, but it keeps going beyond that and eventually produces such incomprehensible effects on the image that you have to shift to a new place of the carbon film and start all over. So there's a sawtooth kind of time evolution of the contrast in the image of the phase shift. And depending on how long it has been since when the carbon film was first evaporated and put into the microscope, these sawtooth ramps change more and more rapidly as the weeks and months go on. So these aren't necessarily bad things. They're just kind of annoying things, and people have been able to work quite well with them. Now, a further point to mention about the VOLTA faceplate is some electrons are lost when the electrons go through the carbon film. That's only about 10% of the electrons, maybe 15%, depending on the thickness of the carbon film. But more importantly, Bart Glaeser and Danev and I have just published a paper showing that there is a further additional linear fall off. We referred to it as a DQE, detective quantum efficiency effect of the faceplate itself, nothing else, not the camera, not the microscope, just of the faceplate. And that's really pretty much not acceptable. The fall off goes down below 50%, down to 40% or so at high resolution. So that represents something that one would really like to improve with further development of technology. The background about the ponderomotive faceplate, I also have to say a little something about that. You might say, how can light cause the phase of the electrons to change? Well, it was predicted already in the early days of quantum mechanics by Kapitsa and Dirac in 1933. And the way that I like to express it is the subtext in the first line here. So a high density of confined electrons, let's say a piece of glass. I'm going to think of a piece of glass as a little object in which there are a lot of electrons and they're permanently kept in that little object. And that high density of confined electrons refracts light, refracts photons. Exactly the opposite is also true. A high density of confined photons refracts electrons. It's not something we normally think of, but Kapitsa and Dirac pointed that out. And was demonstrated experimentally a number of times, generally acknowledged as being the definitive experimental proof, was a paper in 2001 using only 380 eV, electron volt, electrons. So the interaction is extremely weak. You have to have a whole lot of photons confined in a small space to get an appreciable effect. And the first experimental, the effect is greater for low energy electrons. So the experimental demonstration used very low energy electrons. A patent was filed in 2010 by Brian Reed, who was then at Livermore, where they have lasers that are very, very powerful. And he could pack a lot of photons in one space, one area of space, small focused spot. And he got a patent in 2010 to use, as indicated schematically from his patent, a laser that crosses the electron beam going through, it's placed in the gap between the pole pieces of the objective lens, and a lens focuses the pulsed laser, and he envisioned having a pulsed beam of electrons synchronized with the pulsed laser. He used a pulsed laser in order to get enormous photon intensity, but only for a short period of time. Now we, this means Holger Mueller and I, at the initial paper, a number of colleagues, proposed to use what is called a Fabry-Perot cavity to build up the required intensity instead, and that might need only something like a 10 watt or 20 watt, et cetera, laser, using a cavity as a power buildup device and a focusing device. And that's what I'm going to talk about from this point. So the first proposal to suggest to use a cavity as a faceplate in 2010, and it wasn't until 2018 that we finally began experiments inside of a transmission electron microscope. Now this TEM is one that I had purchased earlier for phase plate experiments that I haven't said anything about. I named them, but haven't said anything about them because in the end, they were just as unsuccessful as all the other ones that had been performed since 1947. The microscope was there. The microscope was equipped with relay optics that take the electron beam from the region of the octagon in the middle here, and the Lorentz lens helps relay, is turned on at the same time the objective lens is turned on. Very unusual mode of operation. Relays the electron diffraction pattern down to the next module in the column. And I can point out there are 4 new ports that are not standard at all. I've got my arrow on one. There's one around to the right. There's left. There's one around to the right. So we have extra ports, and there's an extra lens in this part of the module and some beam deflection for alignment. And shown here is a breadboard mounted on the left of the column with a laser beam, and the laser beam is being shot into the cavity that you cannot see, but it's inserted in this part of the column. Now, a little bit astonishing, I hinted at it before, and a standing wave of light is actually easy to be seen in a transmission electron microscope. So if you use electrons to look, you can see light with electrons. The proof of concept of the ponderomotive faceplate was first achieved using 80 keV electrons for the same reason. Lower energy electrons are refracted more by a laser beam, and we didn't have quite a sufficiently powerful laser beam in the cavity to go up to 300 keV. In fact, we did not even get 90-degree phase shift at 80 keV, but this first proof of concept was published in 2019. Now, how do you see light with by using electrons? The answer is to use a Ranschigram. STEM people will be very familiar with this. And for the rest of us, I'll just explain that if the electron beam is focused either above an object, so in the right-hand panel here, we have a laser standing wave represented in panel A as the yellow beads. In this case, the electron beam is focused below the plane of this phase grating, this standing wave, and it produces by interference sine waves of electron intensity quite some distance down from where it was first focused. So you can focus either above or below. Focused above, it's like a point projection microscope. So enough sort of explanation. Don't want to use up more time. Panels C, D, and E are examples of the Ranschigram taken in C, well far away from the laser streak, and you see just a white streak going on across diagonally. You zoom in and you see the maxima and minima of the standing wave. Go a little closer to being in focus or on plane, as people say in the phase plate community. The Ranschigram begins to become magnified as you get closer. You see the standing waves get even closer. It's getting very much magnified. When you're exactly focused on plane with the laser faceplate, then the magnification goes to infinity, and that's the condition. You want to have uniform illumination across the field of view. You can also take images of carbon film and compute the Fourier transforms. That gives you the familiar tone rings. And having brought the electron diffraction pattern on plane with the laser standing wave, it may still need to be shifted to the left and to the right, or X and Y shift. And that is easily done in real time by looking at the real-time FFT and shifting things around until the laser streak goes right through the center of the Fourier transform. I won't spend a lot of time talking about these slides. They're just kind of eye candy that have been put up for the laser specialists. And the point here is to say that the laser beam can be really quite constant, only tiny, small jitter and intensity and average intensity. The temperature of the cavity changes as the number of hours goes by, as the time goes by. It changes by a few degrees. And that causes a change in the wavelength of light that is resonant in the cavity. All of these are taken care of automatically by feedback operations. And the minimum size of the laser focus changes from about 7 micrometers to 8.5, depending upon how much power is circulating in the cavity. That's again due to heating and deformation of the mirrors. These are significant effects in a way, but they're minor. They do not cause any problem in the use as a phase plane. I'll get my cursor active on the screen again. There we go. So here's the net result. This is what we were after. And on the left-hand side, panel A is an example that cryo-EM people will recognize as being pretty typical of what a biological molecule, in this macromolecule, in this case 20S proteasome, looks like with defocus phase contrast. On the right is what it looks like with a 90-degree phase shift, 300 kV, using a laser cavity as the faceplate. Want to thank and acknowledge the lab of Yifan Cheng and particular postdoc Zanlin Yu for providing us already frozen thin grids of of proteosomes, a specialty in their lab over in San Francisco. So this is good. This demonstrates that we get the contrast that we were hoping for at 300 keV. But you can ask, but are the images any good? And so about 5,000 particles were chosen from micrographs, series of micrographs, processed in the usual way of single particle cryo-EM stuff. A lot of stuff going on in this slide. I'll illustrate just some of it. Getting to the good part first, a 3D reconstruction from 5,000 particles times 14 asymmetric units per particle gave a map that went to a resolution of about 3.8 angstrom resolution. In the FSC curve in the middle left panel, the representative examples of different two-dimensional class averages of different particles show very promising features, something we want to look for. Later analysis of the data, a B factor for this reconstruction, approximately 130 square angstroms. The distribution of phase shifts is obtained from analysis of Fourier transforms of all the different micrographs, centered in this case around 75 degrees phase shift. Not quite what we wanted, but close. Now, the resolution of 3.8 angstroms, we're very, very happy with it, but it doesn't match what has been done with defocus. We're not there completely. And we did not really expect, we knew that there was a serious limitation in our current implementation of the laser phase plate. And the limitation is that the relay optics that I described using the Lorentz lens and the special X lens, those relay optics add to the aberration coefficients of the microscope. In particular, the chromatic aberration in this microscope is a little over 7 millimeters. And because of that chromatic aberration, the temporal coherence envelope, this gray curve pointed to by the arrow, starts to roll off at around 3 angstroms, 3.5 angstroms resolution, and limits how much resolution we can get. Now, you can always get more resolution by just collecting more than 5,000 particles, 50,000 particles, whatever. That's not what we're trying to show. We feel no particular urgency about overdoing it in order to show we can go to higher resolution. We think there's a better way than trying to prove a point that in fact would not be very impressive, that we have to use more particles to get higher resolution. Instead, our plan on how to take this forward is to add a gun monochromator, and we hope to be able to do that within a year or so, getting pending funding provided by grant application. And during the time that we're waiting for that to be decided and hopefully purchased and installed, we'll be busy working on automating the way in which the alignment and centering is carried out. I described it in the previous slide, but this is done manually at this point. And in addition, the contrast transfer function does have a streak across the center, which I described, and that's not included in the usual model of contrast transfer function that you find in data processing and data collection software. So that's, we think that's probably a small thing, but it's a very necessary thing. On the right-hand slide, I should have mentioned it previously, compares the temporal coherence envelope function and how it falls off. If we were to use a gun monochromator, currently we believe the energy spread is probably 0.8 of an EV, and so the envelope function rolls off, as I showed previously. But if we use a gun monochromator to cut that energy down to about a third, the envelope function should be quite good out to about 2 angstrom resolution. That's the plan. Then I can talk a little bit about the future, and then that will be it. So the kind of the holy grail of imaging phase objects, weak phase objects, would be to combine spherical aberration correction with in-focus imaging. So as background, if you use spherical aberration correction without a phase plate, all you will get is amplitude contrast. Phase contrast will be 0. And this is the current state in material science, where people are very successfully using spherical aberration correctors in TEM as well as STEM. And the images are necessarily amplitude contrast because there is no phase plate. And I remind you that I started the talk by saying that amplitude contrast provides only about 7% of the signal that is available in phase contrast. So there's a lot of promise. I say it with some reluctance or hesitancy, but there's a lot of promise in combining a phase plate with spherical aberration correction. Perhaps the time is finally right to bite the bullet and combine these two. Now, I used the familiar joke, you better be careful what you ask for, you might actually get it. And then what are you going to do? It's quite challenging to take advantage of the wonderful things one can dream about that would occur if we had a spherical aberration combined with a phase plate. Now, in material science, again, there is no problem to record the images precisely in focus. You just look at the thing with the phase plate on and the spherical aberration corrected and focus until it's right. We cannot do that with biological objects. We have to shoot blind. And if you miss by 100 angstroms or so, you're going to get oscillations even though from defocus, even though spherical aberration is 0. So the depth of focus, or depth of field, sorry, is only about 100 angstroms at 2 angstrom resolution. So you have to really nail the defocus value, and you can't look at it while you're trying to do that. So it's quite challenging. Furthermore, if one thinks of looking at thick objects that are a couple of 100 angstroms in thickness, or even tomograms where the sample is samples used for tomography that are 1,000, 2,000 angstroms thick, there's only a limited slab within a thick object that will be in focus, and all the rest will be out of focus. So these are challenges, and you have to really think through in advance. Do I want to go there? Is it worth doing to begin with? Well, these challenges call for the need to innovate and have novel methods of data collection analysis data collection and data analysis that will fully exploit CS correction with combination with a phase plate. Always lose my place here. There we go. All right, I leave that dream for the future. And as I do, I want to acknowledge all the fantastic people that are part of the team that have made the progress I've been able to report, have made it possible. Holger Mueller on the left is the professor in physics department who knew about Fabry-Perot cavities and lasers, and realized that this would be possible to do in an electron microscope. Even Nagalis, our fantastic colleague at Berkeley, and whose lab where these things are going on, and we dream about the samples we will be able to look at. We already have a couple of alumni, Osip Schwartz, and I've got obstruction in my screen, so I've got to keep moving that. All right, Osip Schwartz has now, was postdoc, he's now moved on to the Weizmann Institute. Sarah Campbell, also a postdoc, has moved on to Honeywell, where she's got even more ambitious dreams of getting a quantum computer that really will work and will help us out. And the current members across the bottom, Jeremy is a graduate student who's been with the project for a number of years, 4 years. Carter is an undergraduate. Carter joined the project 4 years ago as a college freshman, and he's graduating this spring. He is every bit as valuable and productive as any postdoc could be. Excuse me. Jeska is a second-year graduate student, and she's getting into things quite well. Jonathan is a career microscope operator who works at Stanley Hall, looks after Krios and Arctica instruments, but also helps us out a great deal. He's the only one who really knows how to operate the microscope, and he's been invaluable for the work I've shown. Peter Petrov has just joined us in September. He got his PhD at Stanford in optical microscopy, and he's taking the plunge into electron microscopy. Okay, that's it. Thank you very much.
Thank you very much, Bob, for this really exciting development with the phase space. There are a series of questions from the audience. I acknowledge the questions raised in the Q&A box. In the interest of time, I may not be able to cover all the questions. Please stay tuned because we have a discussion period after the second talk as well. Let me start with the questions from W. Myrna. His question is there any value in differing the position of the standing wave at high speed? Do you time average uniform high optical intensity? Wow.
I think the question is more sophisticated than I can understand. Holger, I think, would understand it, but I didn't catch the point of what we, the question was, is there an advantage of doing something with the laser beam, modulating it in time or something like that, that I didn't quite understand?
Yeah, well, okay. Maybe we can wait till the end that WE can chime in to clarify his questions. Okay, good. And then maybe we ask another questions. Would a cold field emission gun provide similar resolution improvement as a standard field emission gun?
Yes, yes, absolutely. We were a bit ambiguous or torn between choosing a gun monochromator versus a cold FEG. I think they would do equally well. In the long term, is what Thermo Fisher would provide for our old Titan, 10-year-old Titan. So we were happy to take either, but in the end we had no choice. Going forward in the future, you have to look at the possibilities on a new microscope. What would you get? Gun monochromator is still kind of attractive because you can get down to 0.1 EV and corresponding improvement in the temporal coherence, whereas a cold FEG without a monochromator is going to be limited at about 0.25 or 0.3 EV.
Okay, thank you. There's a question from Richard Carragher. She asks, are there time-dependent variables that will make the CC correction difficult?
Time-dependent variables, none that I know of. If anybody in the audience has something in mind, please bring it up. But no, I have to say I don't think so.
Okay, thank you. And there's a question from Chris Russo. Can you comment on what you think about the minimum C sub C for the transfer lens that is compatible with the current laser design?
Yeah, so the best that we can get is a CC of about 7 millimeters. We don't know how to beat that with the transfer optics that we're currently using. So I might amplify on this a little bit. The transfer optics are needed because the focus, the laser focus is limited by the light wavelength is very long compared to electrons, and also by a rather small numerical aperture in cavities. So in the future, one could imagine cavities could be evolve and improve to use much larger numerical aperture than what we have at the moment. And then we wouldn't have to magnify the electron diffraction pattern quite so much. So the spot that we want the phase shift, you know, has to, or the diffraction pattern has to be, the size of that has to be commensurate with the size of the focused laser beam. A little bit complicated, disorganized answer here, I'm sorry, but for the moment, present cavities, we're going to be stuck with requiring enough magnification in the transfer optics that we're going to get something like 7 millimeter chromatic aberration. But in many different directions, this can improve in future years. It'll be quite a development project to do so.
Okay. Another question from Risa Parang is asked, what is the mechanical stability during the data collections? Is that very involved after the initial setup, the experiment?
Well, stability is quite good. There is slow drift due to small temperature changes that, you know, we don't see a clear way to avoid that. So at least the way for now is to, again, use feedback to tell when you're beginning to drift and to automatically readjust either the position of the electron diffraction pattern or the position of the faceplate. So we're doing that manually right now. That's not hard to do at all. And it should be extremely easy to automate that as well. We think so. You know, talk is easy. Wait until we do it, then I can say it was easy to do.
Okay. So another question from Santanu Lanka. It's asked, how precisely can you control the synchronization between the laser beam and then the electron beam?
Yes, yes. So just to clarify a little bit, in our implementation, there is no synchronization required. We're not using pulse lasers. We're using a CW laser and a standing wave of light. There's no time dependence here.
Okay. A question asked by Jeff Wula, and it's asked, how exactly does the forward model change in terms of convolution with CTF and DQE? Is there any other extra laser term in the contrast theory?
Just the form of the phase shift. So the ideal form is a phase shift involving only the unscattered beam. We don't have that. We have a laser streak. So we put that into the into what is normally the term involving defocus and spherical aberration. We add an extra term, which is a laser standing wave. Yeah.
Okay, good, thanks. So you mentioned about 0.3 electron volt is needed. Then, well, I mean, the question is why not use the Kofi emission? I think you answered the question. You want to have the Kofi emission, right, Bob?
Yeah.
Okay, good, thanks. Let's see, another question is, can you, by Ali Hussan, could you comment on the role of plasmonic and time-resolved method for phase contrast?
So you're thinking of some kind of a metal object, nanoparticle, for example, and when you shine light on that, the conductor acts like an antenna, and you get a huge light amplification in the near field of the little particles. So you could use that near field and position it at the unscattered beam. That's I think a perfectly good idea. I'm a little bit afraid of it because you get an awful lot of inelastic scattering of electrons from the near field of the near field light field of an object. That's because you can have momentum transfer from the electron to the nanoparticle or the antenna when you're very near. But when it's I'm not saying that's bad. I've not worked it out, but it scares me. I don't want to have inelastic scattering of electrons by the phase plate. In the free space standing wave, there is no loss. There is no inelastic scattering of electrons and no loss of signal. So without exhaustively looking into it, that just seemed a good way to go.
Okay, good. There are still a lot of questions raised in the Q&A. In the interest of time, I encourage the participant will stay on after the second talk. Again, I'd like to thank Bob Glaeser for this excellent and exciting development in the phase space. Thanks very much, Bob.
Thank you.
I turn the floor to Yi.
Let's see.
Okay, thank you, Wah. Thank you. Terrific. I'm would like to switch over now to David Smith, who's going to be our next speaker. I've known Dave, I think it's now 40 years this year when we first met, when he was the hot young electron microscopist from Australia, coming to Cambridge University to run the high resolution facility there. And we published a paper on that work, which appeared on the cover of Nature from that time. Anyone who has been at the Arizona State University Winter School will know Dave's unbelievable enthusiasm and drive for high resolution microscopy. He started off life, I believe, starting with STEM, has been involved with TEM high resolution for many, many years, and much of his recent work has been back in STEM again. So it's my own great personal pleasure to pass the baton to Yi Che, who will formally introduce Dave Smith. Thank you.
Well, thanks, Bob. It's my great pleasure to introduce Dave. Well, Dave, you all know already, Dave was the former president of Microscopy Society of America. And so is Bob Glaeser. So that's why today is particularly honored to have both on stage. Dave, as Bob mentioned, Dave has been really leading as a leading expert on developing high resolution electron microscopy, starting from his time as the acting director, and then director of Cambridge University High Resolution Electron Microscopy Project, moving to Arizona State University. He was appointed as the director for the Center of High Resolution Electron Microscopy. He's a fellow of MRS, fellow of APS, fellow of Microscopy Society of America, and fellow of Institute of Physics. He received many, many honors I don't have time to go into. With that introduction, Dave, please tell us about the exciting topic you want to share.
Okay, thank you, Bob and Yi, for your kind words. I'm pleased to be here. I'm going to accept the challenge presented to me by Bob Sinclair. As he indicated, I started life doing STEM with John Cowley, and my PhD was applications of the STEM. And then for 35 years, I did high resolution microscopy, TEM, solely. And then, as Steve Pennycook would say, I came back from the dark side and I started doing STEM again. So my challenge today is to give you a little bit of flavor of each of those techniques and then see if we can answer this question about anything TEM can do, STEM can do better. And I deliberately, evocatively have the dots and the question mark. So in the beginning, of course, there was Ruska, who invented the TEM, but it was closely followed by Ardena, who very soon after, you'll notice, not many years later, came along with the STEM. But there was a problem with the STEM in those days. We just had a very low brightness tip. We had a very clumsy system for recording images. And so the STEM really didn't go very far for a long time. Meanwhile, TEM flourished in biological fields. The biological scientists managed to find ways to get thin sections, and the physical scientists, material scientists could get thin sections of their metal foils. And then microscopy improved over the years, or the microscopes improved. And then it was a question of proving how good was the microscope by chasing lattice fringes. And Komoda, among others, was chasing lattice fringe resolution on the order of 2 angstroms. And then we get to the 70s, and Sumio Ojima was the first with a 100 kV TEM to actually get what we would call structural imaging. But I want you to notice this was actually the tunnels between the atom columns. This was only at 100 kV structural resolution on the order of about 3.5 angstroms. Well, in the 1980s in Cambridge, we were able, on the COSLET 1 angstrom project, didn't quite make 1 angstrom, but at 500 kV, you get improved resolution, and you can get images such as this on the left and this on the right. And in this case, each of the black spots represents a row of metal atoms. So here we are resolving metal atoms in that structure. Not the oxygen atoms yet, but we are doing structural modeling directly. Well, if we want to improve resolution, of course, the old conventional wisdom was go to higher voltage. And JOL and Hitachi developed higher resolution TEMs. And there's the microscope and rulers lab in Stuttgart. And lo and behold, 1 angstrom was achieved. So the Holy Grail was something that when you were a young graduate student, you could never get 1 angstrom in the electron microscope, an impossibility. And yet, here we are, there's the first zero of the transfer function measured by this optical diffractogram back then, and 1 angstrom was achievable. Not only that, it was possible to really push lattice fringes. If you had a high stability microscope like the microscope of Tonomura, you could even push lattice fringe resolution to beyond 0.5 angstroms. So that was where we were with high resolution TEM around the turn of the century. Well, what about STEM? Well, the Woodstock of STEM was when Crew and colleagues first did direct atomic imaging. It was a 30 kV STEM. It had a field emission gun. That had been, as I indicated, brightness was a limitation on the earlier attempts to do STEM. But once a field emission gun was developed, you had enough brightness to get a very small probe. The probe in Crew's microscope was limited to about 5 angstroms, but it was nevertheless adequate to resolve individual atoms of thorium and uranium and other high Z materials. Around about the same time, in fact, the year I was in the last year undergraduate in Cowley's lab, Cowley came out with the principle of reciprocity that showed us that you could understand CTEM and STEM. If you take the source going sideways to the right, specimen, objective lens, put in an aperture and get your image, consider the STEM as going in the opposite direction. Exactly the same optics, except you're just reversing the direction of the electron beam. And not only that, Nellist and Pennycook and many others pointed out this was incoherent imaging. And so here is the optical transfer function of a STEM. And here is the oscillating transfer function for a TEM. No phase reversals, very important for image interpretation. You don't have to worry about the phase oscillating up and down. Moreover, before aberration correction, TEM and STEM, there was no question which technique provided the highest resolution. Well, what happened in the 1970s was that the manufacturers, inspired by Crew's development and collaboration with Hitachi were able to bring out a 125 kV TEM with field emission. Yes, this is very improved lattice fringe resolution, but the important point for us, field emission TEM. And so at the same time almost, VG realized that they could modify their system and they could also do STEM. And so Steve Pennycook and colleagues came along with VG microscopes, chased by several other people. But the important thing is, here we have a focus probe, we have the sample, we have a large angle annular detector. And Z contrast meant that you were able to resolve the high Z atoms. You had sufficient brightness to do that. Well, low Z atoms were not visible in this particular case. My mouse has gone to sleep, excuse me. It has these little problems from time to time. Okay, there we go. But low Z atoms were not visible. But what did Chisholm and colleagues show? That, and this is according to reciprocity again, that if you use a small collection angle, typically small meant about 1/10 of the incident angle, it was possible to observe oxygen atomic columns in STEM. So these spots here are actually the oxygen atomic columns. So yes, even in, it was just around the turn of the century actually, it was possible to observe low Z materials in phase contrast bright field STEM. Well, what also happened in around about the turn of the century in the 1990s, it was realized that there were several different approaches to aberration corrected EM. And there are 4 major ones, all of which work very well, as I'm about to show you very briefly. You can do online or indirect software. You can do a focal series reconstruction to take out the oscillations of the transfer function. You can do off-axis holography to also take out those oscillations. And then we have the online or direct hardware approaches. And so here is in 1992, Kuna and colleagues with a 200 kV fake TEM, taking a focal series. They were able to look at this yttrium barium copper oxide, and they were able to see oxygen atomic columns in the presence of high Z atoms for the first time. And O'Keefe and Schafhorn and colleagues actually followed in their footsteps at 300 kV, and they were able to see, this is a fact that people seem to have lost track of, 300 kV FEG TEM with exit wave reconstruction, the lithium atomic columns were resolved. And it was very tedious at the time, but I would say that these days with fast detectors and very fast computer programs, you could take a very large area of field of view like this in the TEM and do the reconstruction in the matter of certainly minutes, maybe in 10 to 20 seconds. So don't lose sight of the fact that exit wave reconstruction is a very powerful technique that is applicable to a lot of the things that we might be hearing about in the recent past. Lichter and Orchovsky were able to use holography, and here they are looking at some silicon dumbbells, and here we have the dumbbells resolved in the amplitude image, and we have the dumbbells resolved in the phase image. So electron holography surmounts the resolution limits of electron microscopy. At the same time, Haida and Rosa and colleagues were able to come up with CX correction in the TEM using the hardware approach. Comparatively simple, we have 2 hexapoles, we have a doublet and a doublet. It just means that you increase the length of the column by about 30 centimeters. Millimeters would be great, centimeters. And you're able to get individual atomic columns once you get hardware correction. And Jha and Urban showed this very interesting case that, again, people seem to have forgotten about a bit. They were able, way back in 2003, they imaged with negative CS. And if you look at this image of strontium titanate in the 110 projection, and you look at this row here, these faint spots, the faintest spots are actually oxygen atomic columns. And Jha and Urban were able to see when there were missing atoms, missing oxygen atoms. So not only were they able to resolve and distinguish the oxygen atomic columns of low Z, they could even tell you when some were missing. And an extra benefit for holography that people weren't anticipating at the time, correcting aberrations using holography was quite tedious, taking out the astigmatism, taking out the coma, XY in both cases. If you did the aberration correction first, as Hannes Lichter and colleagues did, they were able to get better phase imaging to the extent that they could start counting the gold atoms in a column. Well, here is CS correction in a STEM, a little bit more complicated, but nevertheless, Andrei Kravanik and colleagues had learned how to do the corrections using in their GIF. They have octopoles and quadrupoles, but it's quite easy to add the corrector just above the condenser lenses in a VG column. So here's the gun chamber at the bottom, condenser lenses, the corrector is added, and then you have the rest of the microscope easily added on upwards. And so here is an early result from the microscope in Batson's lab at IBM, 120 kb. He was able to see single gold atoms on a thin carbon support film. And Jimmy Liu and others have pointed out one of the advantages of STEM is that you now have a lot of flexibility. You can change the size of the aperture. You can just do bright field. You can have a large angle bright field, annular bright field. You can have various flavors of high angle annular dark field, medium, low angle. You can have annular rings. And so this gives you lots of opportunity to do some very interesting microscopy. So for example, Fiddley and colleagues showed that they could get low Z atomic columns visible in annular bright field. And so here is the dark field, high angle annular dark field, no real sign of the oxygen columns. Here is the structural model, but if you look at the annular bright field image, you see spots here and here, they correspond to the oxygen atomic columns. Same thing down here in strontium titanate. You can see the oxygen atomic columns in the strontium titanate. And moreover, just a few, well, the next year, Oshima and colleagues were able to image individual lithium atomic columns using annular bright field imaging. So this is interesting, a little bit of the who came first or whatever, but the important message for us is that we can get visibility of low Z atomic columns in both TEM and STEM. So in the company of higher Z atoms. Well, the benefit of going to lower observation was shown to us by Andrei Kravanik and colleagues by doing AC STEM at 60 kb. You've seen this front cover of Nature, I would guess, probably one of the most rapidly and highly cited papers in electron microscopy history. You can see the individual boron and boron and nitrogen atomic columns. You can see some oxygen columns here, and then there are some carbon columns as well. So atom by atom analysis, you could look at low Z elements without appreciable damage by going to low voltage or low electron energy. But I want to point out, this is a recent result from Ute Kaiser's microscope in where we have the SELVA project, which is a CSCC corrected. One of the problems with a lower voltage microscope is the delta V over, or the delta E over E becomes larger. But if you can correct the C sub C, then you get improved resolution, even down at 40 kb or 20 kb. And in this case, Lehnert and in Kaiser's laboratory were able to show that they could see in this line scan, you can see here we have two tellurium atom columns and then 1 and then 2. So they were able to reveal missing tellurium atoms. Okay, so there is a little overview of what can TEM do and what can STEM do, but I want to go back to the basics. When are 2 points resolved? So we have the classic Rayleigh configuration where we get light from one source and light from another source. When do they overlap? What can we resolve? And to the best of my knowledge, here is how to have STEM imaging 300 kV in Okuhara's laboratory. The sample is very well known, so there's no dispute about what is going on. It's a gallium atomic, it's a structure of gallium nitride in a 2-1-2 projection. Here is the initial image, a little bit of averaging going on here, and not quite Rayleigh criterion, but at least according to Sparrow criterion, maybe you can resolve the atomic columns of gallium. We're not seeing the nitrogen columns, but we are seeing the gallium columns. Okay, so what can you do in TEM? Well, this is a result from the aberration corrected 1.2 million volt microscope in the Hitachi lab at Tonomura. And this is gallium nitride again, structure's well known. Here is the atomic structure. Here are the images. And again, if you want to do a line scanning and say, well, yes, the peaks are just resolved. But now comes an interesting question, because we're getting this high, very sub-angstrom resolution in TEM and STEM, but atoms aren't that close together. And this is interesting. Here is a structural model of gallium nitride in the 4-1-1 projection. And you'll see that the atoms we're actually resolving in this projection are actually half of the unit cell distance. They're actually 6.5 angstroms nearly apart. And so in projection, we're getting very high spatial resolution, but we're not actually resolving atoms that are that close together. Well, how can we overcome the resolution limits? Tychography is the flavor of the recent microscopy community. Cali and Liu and also Nellist and co. Started doing some STEM observations back when, overlapping convergent beam diffraction pattern disks, and then reconstructing. And here is an example, very important example, resolution limit 4.2 angstroms, the information limit after taking into account the envelope functions about 3.3 angstroms. Okay, so 3.3 angstroms would be pushing that microscope, but they're able to resolve as it were, the silicon dumbbells with a spacing of 1.36. And of course, David Mueller has now wonderfully started to use these MPAD, and he's applied tychography in 4D STEM to aperiodic objects. And so in this case, it's a bilayer, so the atoms aren't that close together in projection. They are very close together. They're 0.42 angstroms in this particular case here. This is only at 80 kV. The point resolution or nominal resolution of the microscope is on the order of just under 1 angstrom, and yet you're able to push to 0.4 angstroms. Can we do better in STEM and TEM? Well, it depends on the question. And so here is a case from Andy Yankovic and colleagues where they did some non-rigid registration, took a focal series, well, not a focal series, an image series all at the one focus, reconstructed. And the important thing for us here is that Andy was able to get picometer precision in the locations of the atomic columns, and he was able to count the number of atoms in the individual columns. So we're not offending resolution limits here. We're just talking about precision on the picometer scale. And so can we do that in TEM? Well, Sandra Van Aert and colleagues were able to use aberration corrected TEM, and they did an exit wave reconstruction. And here is the phase, here is the amplitude. And if you follow through with their manipulations of the data, at the end of the day, they were getting precisions of the atomic column positions across this twin boundary approaching the picometer scale. So I choose both this example and the previous one as examples of what can be done with TEM and STEM. But if you are trying to locate atomic column positions with high accuracy, then you can go far beyond the resolution limits of the microscope. So these days in TEM and STEM, lots of things going on. Data acquisition, we have direct electron detectors and segmented detectors, and we have various interesting processing methods. We can do phase retrieval, 4D STEM, we can do tychography, we can locate atoms, we can do in situ gas liquid environments, cryomicroscopy. These are all topics for future discussion. I just want to take a few minutes to talk about Lorentz microscopy and DPC. This dates back from John Chapman, where he was interested in looking at magnetic domain walls. And in this case, John pointed out that if you have a domain wall, you've got the magnetic field pointing in different direction, opposite direction in plane, you take an image slightly out of focus and you will get contrast across the domain wall. Well, this has been taken a lot further recently, for example, with McLaren and colleagues, looking at an anti-phase boundary in doped bismuth ferrite, looking in what is called by Law and colleagues DPC2, where they're looking at, electric fields. No time here for details. But now let's see if we can push it even further. And Shibata and colleagues did this. They said, let's scan across an atom column. So here is what you would get on your segmented, your split detector here. You would get contrast on equal amounts. But when the probe goes across the atomic column, the electrons are deflected and you get more intensity on one side than you do on the other. And when you pass across to the other side, then you get more deflection on the first side compared to the other side. And here is the line scans that you would get in your X and Y detectors. And the important thing is you will get this asymmetric profile. And what Shibata and colleagues showed was they could actually get atomic imaging with their DPC annular shaped quadrant detectors. And so this has been taken a lot further, for example, by Tim Pennycook and colleagues in Nullis Laboratory in Oxford. Very interesting here, this is their bright field image with their pixelated detector. Here is the annular bright field image, which doesn't really show you very much at all. And here is the annular DPC, and here is the DPC. And it's an advantage of using these pixelated detectors, as shown also by Mueller, that you can choose any combination of the transmitted signals to make up your final image. And this is, for an example, a comparison of Wen and colleagues where they did segmented DPC. This is the angular dark field, and you can see the molybdenum and sulfur columns. Over here in the phase image, you can see the sulfur and molybdenum. But now you can actually see structure in the carbon, not visible in the annular dark field part of the signal. But if you take a phase part with this pixelated detector, you can now get information about the carbon as well. Muller-Caspary et al., I've not got time to tell you about it, but they're doing momentum resolved 4D STEM. They're able to look at polarization fields. Achtel et al. Were able to look at sub-angstrom electric fields using 4D STEM. And Colin Ophis has put together this wonderful review paper. I draw all of your attention to this particular paper. He's overviewed the whole field of 4D STEM. There's the picture I showed you a few minutes ago from Nallist and Rodenberg. Here is Dave Mueller's picture. Here is Tim Pennycook's picture. And here are different examples of how you can retrieve phase information based on overlapping beams. But I wanted to walk you back briefly to say, well, Dave, are you pointing us away from TEM and really going back to the dark, coming away from the dark side and saying there's no hope for TEM? Well, here's some interesting work of Jar and Andreas Thust in Jülich, where they took a single shot with aberration corrected TEM. No time to go through the whole 9 yards here. This is the initial image, but they were able to get the surface topology of this magnesium oxide from a single shot in aberration corrected TEM. I'd also point out Bob and colleagues, as well as Francis Ross in one of the previous talks, you can do dynamic in situ chemical reactions with AC TEM. Here's a case where we're looking at the oxidation and reduction of this platinum particle. And I also point out this very interesting example from the work of Hannes Lichter and colleagues back when, sorry, not from Hannes Lichter, from John Cummings and Wally, where they were looking at, here is a carbon nanotube that's actually field emitting. Could STEM get any useful information from that? Look at the incredible reconstruction of the three-dimensional electric field surrounding this carbon nanotube. Well, I take this slide from Dirk van Dijk to point out that if we're worried about what is the ultimate resolution in our different microscopes, the resolution per se is not the only thing we have to take into account. For example, all atoms will scatter more and less to high scattering angle. The atoms are vibrating, and so information will be smeared out at higher scattering angles. The electron microscope may not have these oscillations anymore that it's aberration corrected, but sooner or later you are going to be limited by the envelope functions, be it spatial coherence or more likely chromatic effects, the beam spread, the beam energy spread. And eventually you can overcome this problem of the detector by going to higher and higher sampling spacing. So here is what Mike O'Keefe showed us, that if you're looking at silicon, for example, in a 116, and this is the Debye-Waller factor at room temperature, and here are the resolved columns or not. And if you start going to higher temperature, then you'll see that the ability to resolve these atomic columns is diminishing. So this suggests that if you want to get the ultimate resolution in a microscope, then maybe you better think about going to lower temperature. Pushing the physical limits. Well, the microscope of Tonomura's was very, very stable out in the deep countryside in Japan, very well isolated from just about any possible means of disturbance. And this is an interesting example, I think, and anyone online who has a better example, please correct me. They actually did a double exposure of the diffraction pattern. They have a beam stopper. So this shows the diffraction pattern. And then they put the beam stopper in, and they got interference between the bar 826 and the 8 bar 6 bar 2 reflections. And here is their result. You stare at that for a while and say, yeah, I guess I can see the lattice fringes. These lattice fringes are 19.6 picometers. To the best of my knowledge, this is the finest raw spacing that's been observed in the electron microscope without any processing, okay, without any processing. If anybody knows of anything better, I try to keep track of these things. Please do let me know. So now I say, well, I've completed the circle. I've gone back to the bright side. I've come back from the dark side, and now I'm doing high resolution STEM. We have a very well shielded environment. We have thermal stability. We have vibrational stability. We're well away from sources of EMI. And so here I was, peace and quiet, one Sunday night in July of 2017, and I'm doing large angle bright field. For the students in the audience, I just want to point out that if you do large angle where you have the collector angle about the same size as the convergence angle, the bright field image is almost the inverse of the dark field image. And so it is directly interpretable. It's not a phase contrast image. And so these spots you see here haven't quite fixed up the coma and the astigmatism. But nevertheless, here I was minding my own business late on a Sunday night, peace and quiet, when all of a sudden things went crazy. So this is, you have a 10-second pause. Now you have to tell me, I know the answer. Can you propose the reason for this bizarre behavior? Okay, I'm counting down 3, 2, 1, 0. It was in the middle of a thunderstorm and I didn't realize I was so busy concentrating on tweaking the coma and astigmatism. And then I thought, I'm not touching the microscope. What is going on? And then I'm aware of a faint noise. And I go outside. I had to go through 4 doors. That's how isolated we are from the outside world. And I find we have a thunderstorm, bolts of lightning, thousands of amps going to ground not so far away from where I'm located. And so even with the best of times, with the best TEM and STEM, and you are doing all the right things as far as taking account of all of these factors that might affect the resolution, there can be sometimes factors beyond your control. So coming back to my original challenge, anything TEM can do, STEM can do better, I would have to say, my answer would be, well, what problem do you want to solve? And really how? Sometimes this will depend on which laboratory you happen to be in and whose software you have available. But these days, there's a lot of openware out there. Software is becoming available. So if you have the right microscope, albeit TEM or STEM, maybe you could do a focal series reconstruction. Maybe you can do 4D STEM. Choose the particular technique to solve your problem. And so I leave this as an open question. Anything TEM can do, STEM can do better, but not always. Okay, so there we are. I hope you enjoyed the talk, and now I'm open to some questions.
Well, thank you very much, Dave. This is a really amazing overview on STEM and TEM comparison. Very, very nice. I'm sure students will benefit a lot of this whole, really comprehensive analysis. So I would like to encourage the audience typing your questions in the Q&A. I will start by asking Dave, I think your conclusion is very clear. Depending on the problem you want to solve, you want to pick the right technique for it, whether it's STEM or it's TEM. Let me ask you the first question. Nowadays, this is of course very, very exciting research on the single atom catalysis. You show one of the early picture. I was stunned, and several decades ago, people can already resolve single atom using STEM technique, using STEM, HADAF, right? Now, thinking about that further, this single atom have atom A, atom B, many single atoms together. Some of them are closest together. What's your thought? How can we not only resolve the single atom spatially, but also figure out what element each atom has? Is really having, is that already possible, already done, or what does it take if it's not done yet to really get there to resolve single atom elementally distributed randomly?
Yeah, that's an interesting question. And I think that the people who grew up with STEM, looking at single atoms, some of my colleagues who may or may not be here, they continue to use STEM to look for their single atoms. But it seems to me it would be interesting now, and I think other colleagues are looking, for example, using TEM. So there are a number of examples of in situ microscopy where people are trying to see what's happening during reactions, and you can see the atomic columns, and you can see the single atoms bouncing around on the surface of these small nanoparticles. And so one of the advantages, of course, of using TEM compared to STEM is the total intensity of the localized beam is much, much smaller because you are averaging out the whole beam over a large area. Whereas when we're doing STEM, you're really zapping each particular area of the sample. So I would have to say that for this individual single atoms, it would be interesting, and I would encourage the colleagues who are listening maybe to take a look at some of those special catalysts and do some aberration corrected TEM instead of aberration corrected STEM? Very good question, and the jury is out.
Yeah. So a question from Royal Christopherson asking, could you say something about aberration collected STEM versus AC STEM for beam sensitive materials, for example, beam sensitive minerals? My impression is from Royal that AC STEM with the new direct electron detector will be better simply because of the shorter beam exposure time.
Again, I think it would be very interesting to do a trial in one of these doubly corrected microscopes to look at the same sample with both techniques, because we are zapping the sample very hard in STEM, but the total dose in that area may not be any more than it is in TEM. And so we do have the advantage with very fancy fast detectors. These days you can do TEM in situ reactions with a very fast, I'm not going to say the names of any particular companies, but you can get 2,000 frames a second. And so you can accumulate the dose very slowly in TEM, look at a large area. And that may prove to be the most profitable way to go forward. Of course, the advantage, and I don't need to tell most of the people listening of TEM, is that you can do this single shot or multiple shot very, very quickly over a large area. Whereas when you're doing STEM, you're going to take 10 seconds, 20 seconds to do the scan. And so lots of things can happen in 10 or 20 seconds that won't happen in a fraction of a second or within a few seconds in TEM. And so if you really want to follow the detailed progress of a chemical reaction, TEM is the way to go. STEM is not going to help you.
Yeah. So David, I think your answer also answered a couple of questions related to this topic. Let me ask you a different one. This is from Centennial Lanky. We have disadvantage of HADAF due to signal to noise ratio. As we have very less signal in HADAF mode, we get a pooled, signal to a noise ratio. How can we overcome that?
Sorry, I'm looking at that.
Oh, the audience mentioned this pool signal to noise ratio if we use a HADAF technique. How do we overcome this?
Well, I think these days, if you have a pixelated detector, you are able to collect the signals from very large areas of reciprocal space at the same time. And then you could choose the area that you're interested in to optimize the contrast that you're trying to. I mean, it's horses for courses, to coin a phrase. Choose the particular imaging conditions according to the particular information you want. So I don't think, yes, HADAF has perhaps a disadvantage for signal to noise ratio, but you don't always have to use HADAF if you're using a STEM. You've got all that information on your pixelated detector. Combine it in a very clever way rather than saying, I'm only going to do high angle angular dark field. Okay?
Yeah, one more question, Dave. Perhaps the most fundamental difference between TEM and STEM is the influence of inelastic scattering and chromatic aberration. Perhaps this is less relevant for the ultra thin materials, but could be a major factor for cryo, TEM or EM type, because thin samples is harder to be available. How do you see this difference?
I think that this is an interesting question that people are addressing, for example, in UISH and in where they have CC correctors, and they are able to take out the effect of the inelastic scattering. If you do take out a lot of the inelastic scattering, you may be losing signal in thicker samples. But I think a CC corrector might be the way to go to look at thicker cryo images.
Yeah. So Dave, I'll ask one last question for students. with the technique, the technology advancing so fast, so quickly, you know, correctors, different detectors, how do you see the education in these areas evolving? And this is to help, certainly help students, right? To help, you know, undergrad and graduate students of all these advanced techniques. So what's your suggestion? You know, how can students follow all this development, fast development?
It's very, very difficult. And so this is a challenge for John Mansfield and M&M, where we are trying to get some of our colleagues to give overview papers that are useful to the students. I mean, of course, I can put in a plug for the ASU Winter School for high resolution microscopy, but that's not feasible for everybody. But M&M is making a point of trying to have, for example, we have in the pipeline a very comprehensive review from Jimmy Liu on the applications and advances in scanning transmission electron microscopy. There's the review paper I already referred to of Colin Ophis. And so these sorts of places provide that insight. And of course, the students should make a point of going, albeit maybe virtual, to the annual M&M meeting, where there are opportunities for tutorials in these various important topics.
Thanks, Dave. I also like to add the reason we started the Electron Microscopy X Symposium is for the purpose of utilizing the expert like you and Bob Glaeser to give the lecture broadcasting around the world to also for the educational purpose. With that, I would like to thank you very much for your fantastic talk. I will circulate this back to Bob Sinclair.
Could I make one more comment? I did very carefully, and so you do make these lectures available online to the people who attended, that just about every single slide I have given the original reference down in the bottom right. And so the students are encouraged to go and look up those papers so they can see for themselves these developments, because most of those papers were historical landmarks, as it were. Do go and take a look at those papers, okay?
Fantastic, Bob.
Yeah, thanks for leading that interesting discussion, Yi. And Dave, fabulous talk. Bob Glaeser, fabulous talk. Dave, of course, you know, this debate within the electron microscopy community about TEM versus STEM will be ongoing. And but I was very interested by your approach to that last question. I'm doing a regular TEM course this year, and talking about Abel spheres and Abel sphere construction and diffraction and imaging, and now with all the STEM techniques as well, it's almost overwhelming that one needs a 1-quarter course is not enough. A 1 semester course is not enough. And I think that the Microscopy Society of America putting together these modules and with the M&M publication, I think is one way to go, but one still needs the basics. And as you know yourself, I believe the TEM is different from many other data acquisition machines. You have to really fight and interact with the microscope and the specimen in order to get the best data. And of course, the new STEM techniques allow post facto recovery of information, which you may have missed as well. So it's the whole developments in the field have been remarkable over the last 10, 20 years and continue to be so. Thank you, Dave.
My pleasure.
So I think at this time, we will conclude for this week, the public session. We will meet again March 1st, the first Monday of March. And we'll have Brian Kabilka from Stanford Medical School, who will talk. And from Europe, Eva Olsen, who's the General Secretary of the International Federations of the Societies of Microscopy, will present her work on in situ and piezoelectric holders. So that will be quite different from the talks we've had today. But of course, our field is so broad and so exciting these days. We hope that we're bringing a little bit of excitement to those people who are locked in at home as we are here for the foreseeable future. So thank you. We'll finish this session and we'll remain online for a few more minutes for people to address the speakers directly if they wish. Thank you.
Dave and Bob, it's